This video is about the factors that influence the various patterns that we find in the periodic trends. So for example, why do atoms get larger as you move down the periodic table? Why does electronegativity increase as you move across the table? Before we talk about the specific trends, let's talk about this page that you're currently viewing. What you can see is that you have three electron shell diagrams for atoms on the periodic table. And of course, you can identify these atoms in various ways. One way would be the number of protons in the nucleus. Here we have 11, 17, and 55. So that identifies each of these atoms as sodium, chlorine, and cesium. But of course, you could identify these atoms in another way. You could basically find their address on the periodic table. Now by that, what I mean is every single box on the periodic table is an intersection of a particular group at a particular period. And each of those locations has different information associated with it. For example, the periods we know are equivalent to the number of energy levels, and the groups are equal to the number of outermost electrons. So in the case of this first one, the address that I see is this atom has 3 energy levels, so it's somewhere in period 3. So we've gone from 100 choices down to 18 choices. And then of those 18, it's the one that only has one outermost electron. And that means that it's in group 1, and that identifies it as sodium. Now you can make similar arguments and find the location of the chlorine atom and the cesium atom. The other thing in these diagrams that I want to point out is that there's something not entirely realistic about the diagram. Certainly it's a much simpler view of the electrons and the electron cloud than, say, electron configuration, which is a very specific description of where every single electron is out in the cloud. But what this diagram does, it makes it look that all the energy levels are equivalent except for the fact that you get further and further away from the nucleus. So when I draw this on my iPad, or if I was in the classroom with you and I was drawing this on the board, it looks like each electron shell is just an incremental distance away from the nucleus. And this really isn't accurate. In fact, because of the scale of the atom, we could never do the atom justice on the screen. So if I were to place the smallest dot I could to represent the nucleus, here on the center of the page, let's say, the first shell is already off the screen. And the next one is not some incremental distance, but is another large distance away from that. And the same with the next one. In fact, if we were in the classroom, the first shell would be off the board, and the next one would be outside of the building. So the relative space between each shell is really quite large. This sort of diagram doesn't make it look like that. It looks like it's just a small incremental increase in size, and it's not. And that's really important for understanding some of the patterns and some of the trends. So as you add electron shells to an atom, you're talking about a rather huge, rapid increase in size, not a small incremental increase. The other thing, if we could scale this down so it fits on the screen here, is the spacing or the distance between the shells. And I'll do my best to represent this, but what we actually find is something closer to this. Where the distance between the shells gets progressively less and less and less. So the effect of adding another shell becomes less and less dramatic the further down the table you go. Now that's a level of precision that honestly is not really going to be relevant for our discussions, but it is a matter of fact. Explaining the patterns for the atomic radius trend is really the easiest of the three. And what I want you to notice is that the explanations for the patterns is the same for all three trends. So as soon as you master why atomic radius does going across and down, you can use those same explanations to understand why electronegativity does what it does and ionization potential behaves the way it does. So let's start out by just reminding everyone what the pattern was. Atomic radius basically decreases as you go across the table and increases as you go down. But why is that? For these discussions, let's look at the same three atoms. So we're looking at sodium and chlorine because they're in the same period. They have the same number of energy levels. And we're looking at sodium and cesium because they're in the same group. They both have one outermost electron. So going across the table, why do atoms shrink? Well, if the size of the atom is dictated by the size of the electron cloud, I could see why many people would expect that both the sodium atom and the chlorine atom are basically the same size. And you know what? They are very close to the same size. But if you had to answer the question, what happens to the atomic radius as you move across the table? Do atoms stay the same in size, get larger, or get smaller? You would be forced, when you saw the data, to say that atoms basically get smaller as you move across the table. And there is a definite reason for that. So we're starting out with two atoms that are very close to the same size, but then we have a certain feature that's acting on both. Out in the cloud, you have negatively charged electrons. But remember what you have in the nucleus, positively charged protons. There's 11 in the sodium and 17 of them in the chlorine. So which of these two nuclei is basically more positive? The chlorine. And what kind of charge can attract negative charges? Positive charges, because we've agreed that opposite charges attract. So the more positive a nucleus, the more aggressively it attracts negative charges. And in this case, that means that the nucleus of the chlorine is going to more aggressively attract the electrons out in its cloud. So all the electrons in the cloud of both of these atoms feel this attraction. And frankly, that's part of what keeps the electrons orbiting around the nuclei in the first place. So here's, let's say, the attraction felt by this electron to its sodium nucleus. And let's use this arrow to represent the attraction felt by these electrons by the chlorine nucleus. So because the chlorine nucleus has a greater nuclear positivity, it exerts more attraction to its electrons. And basically, when you're attracted to a thing, don't you get closer to that thing? Even people act this way, right, folks? So this forces that outermost energy level of the chlorine from its original position to a little bit tighter position, to a position a little bit closer to the nucleus, and that shrinks the atom, and that makes the atom smaller, and that's why atomic radius decreases as you go across the table, because of increasing nuclear positivity. But let's now consider what happens as you go down the table. As you go down the table, we've agreed that atoms get larger, and they get dramatically larger, because remember, every period you move down the table, you're adding another energy level, and that is a large increase in size. So if I'm going to compare sodium to cesium, well, cesium has 3 more shells, right? It's much, much bigger than the sodium. So of course, the addition of more energy levels as you move down the table explains the increase of size of the atomic radius. All right, so those explanations, in large part, are going to function as explanations for the other two trends. So let's look at those.